Okay, Bismillahirrahmanirrahim. In this video, we are going to go through lesson 6, which is on three-phase circuits. The material that we learn from this lesson will be useful for us when we look at three-phase AC machines, which are three-phase AC generators and three-phase AC motors later on. And here is the reference for this lesson. And here are the contents of this lesson 6. So first we look at the introduction, then generation of voltages and currents, phase sequence, voltage and currents in two different configurations, i.e. Y and delta connections, then the power relationships, and finally the analysis of balanced three-phase systems. Okay, from this slide, what we really need to know is that three power systems are very commonly used because of two main reasons. First, it has a higher power density, and second, that it has a constant power delivered to the load instead of pulsing as we have with single phase systems. Okay, this slide is on generation of three-phase voltages and currents, and on the yellow area here we can see that there are three voltage supply, or they are basically representing three single phase generators, and each of them generate this voltage with the same magnitude, which is square root 2 times V. However, they differ in the phase angles. For each two consecutive phases, there is a phase angle difference of 120 degrees. Now, if we connect a load for each of these phase generator, as illustrated on the right hand side, on the lower right hand side here, then a current will start to flow, and similar to the voltages, the currents are of the same magnitude. However, again, they differ in the phase angle by 120 degrees. The equations of the currents are given in the upper section of the slide, and as I said before, they all have the same magnitude, and but they differ in this the phase angle. The magnitude is simply given by the magnitude of the voltage divided by the impedance. Okay, now if we remember, in the previous configuration of the three single phase generators connected to the load, for each of them, I can draw them again here. For example, this is a single phase generator, and then you connect a load to it. You can see for each of this loop, we will have two lines. 1, 2. The written line becomes the second line. So when we have three pairs of this, in total we will have 6 lines. Okay. However, we can change the configurations that all these three single phase loop can share the same written line, as illustrated in the figure on the left hand side here, shaded in yellow. You can see this is the three single phase system, but now they are all sharing the same written line, which is this line here. that I draw box around it. Yeah, so this is the written line, and then but we still have the same functionalities. For example, for the first phase, this will be the loop, yeah, VA. Okay, and then you also have this second line, second one. Okay, which color should I choose here? It's dark blue. So this will be the second one. Okay, and then surely you can work out the third one. Yeah. So you still have this three single phase system connected together. However, they are sharing the same written line, and then now the total line that we need is only 4. Yeah, 1, and then 2, 3, and 4, including the written line. Okay, and so instead of 6 lines as we had before with the previous configuration, with this configuration we only need 4 lines. Okay, now in this slide that looks a bit busy, we want to work out what is the value of the current, yeah, or the expression of the current that goes through the written line. Yeah. If you remember in the previous slide, we saw that all the 3 loops are sharing the same written line. So there are basically 3 currents flowing into or through the line. Yeah? And these currents are IA, IB, and IC. So the total of these 3 currents is the current that actually flows through the written line. Yeah? And then we can substitute the value for each of these currents, yeah, that we know already, IA, IB, and IC. Okay, and then you can then try to simplify this expression, and then you use some trigonometric identities. Then finally you should be able to simplify all this expression into a simple one, or even actually it's you will get a value, yeah, which is the total of these currents is actually 0. Okay, so again the total of these 3 currents, or the current that flows through the written line, is actually equal to 0. Yeah, so there is no current basically. Okay, so as long as the 3 loads are equal, the written current through the written line or the neutral is actually 0, and therefore we have what we call as a balanced 3-phase system. Yeah? Okay, and then since this written current is 0, yeah, which is the current that flows through this shaded area here in the diagram, because this is 0, then actually we can remove this physically. We can remove the line physically, because in reality there is no current flowing through that wire. Yeah? So we can remove. So as a result, we've got this 3-phase system as shown on the right hand side, and then the system will still work, although now we only use 3 wires instead of 6 that we had originally. So we can save a lot of materials in this case. Yeah? And this is why we say that we can, with this 3-phase system, we have a better power density. Yeah? Because by using only 3 lines, we can deliver the same amount of power as we use for 3 in the separate single-phase systems where we have to use 6 lines. And this slide is showing us there are two different sequences, phase sequence. Yeah, you can have VA, VB, VC, or you can have VA, VC, then VB. Yeah. One of the possible effects of this is that in terms of motor, if you apply the phases in different sequence, that you may change the direction of the rotation, for example. Okay, and then each generator and each load in 3-phase system may be connected differently, either Y in Y connection or in delta connection. Yeah, as can be seen from the figure. Yeah, so the one on the left hand side here is a Y connection. Yeah, because it's resembling a letter I upside down, and the one on the right hand side is called delta connection. Yeah, you can see it looks like this Greek letter delta. Okay, and the delta connection is possible. Yeah, because the total voltage, this, because of the 3-phase, is actually 0. So there is no short circuit current. Imagine if the total voltage is not 0, then current can be flowing through the loop, which is not good, because the resistance will be low, and then relatively low, and then so for even a small voltage, you can have some significant current, and this current is not is flowing continuously, and therefore it's going to be wasted. You end up with an inefficient system. Okay, and then here it says that the voltages in a given phase are called phase quantities, and then between lines are called line quantities. So for example, in this the one on the left hand side, in the Y configuration, phase voltage, for example, is this voltage here across this. There's a VAN, and then this is another one, and there's another one. But the line voltage will be the voltage between the lines. So for example, this one here, this is going to be a line voltage, and this is another one, and if you look for the third one, it will be between these two lines. Okay, and then for the delta connection, phase voltage, an example would be this. This is phase voltage. There's another one, and this is the third one, and the line voltages are this, and this. Okay, so you can say as VAB, VBC, and VCA. Okay, so those are the line. The line and the phase voltages. How about currents? We've got phase current. For example, on the left hand side will be phase current that's flowing through here of phase A. Maybe I should use different color. So I can use this one. Okay, this is phase current, A, this yeah, and there's another one, right? And then for the delta, again this will be phase current, yeah, all this, yeah, flowing through each phase. But how about the line current? Yeah, line current for the Y connections will be the current that flowing through the terminals. Yeah, for example, this one is line current A, and that's line current B, and that's line current C. Okay, right? And then you can see that, for example, if you look at phase A of phase A of the phase A of this one configuration, you can see these two currents. Yeah, this is the line current, and this is the phase current. They are flowing through the same path. Yeah, exactly the same path. So those two currents will actually be the same. Yeah, and then similarly for the other phases, phase B and phase C as well. I.e., the phase current and the line current for the Y configurations, they are all the same. Yeah. But it will not be the case if you talk about the delta one. Yeah. The line currents will be different from the phase currents. Okay, so what about the line current for the delta configuration? Again, the line currents are the current that flows through the terminals. Yeah, so you've got the. Okay, now on this slide we want to find what is the relations between the phase quantities and the line quantities, i.e. for both currents and voltages. And then for the currents, as I described on the previous slide, that the currents, yeah, the line currents and the phase currents are the same for the Y connection. Yeah, you can refer back to the previous slide in case you forgot about the why they are the same. Yeah, and then how about the voltage? Yeah, the voltage, the line voltage is again the difference of the voltages on at the two terminals. Yeah, for example, VAB will be the difference between VA and VB. Yeah, so VAB is equal to VA minus VB, and the voltage for each of these will be the phase voltage. Yeah, this is the phase voltage, the magnitude is phase voltage, and similarly for VB as well. Again, and the difference in the phase angle, one is 0 degree and the other one is minus 120. Yeah, and then if you then simplify this equation, you should find that VAB is equals to this expression here. Okay, and then if you just take the magnitudes, yeah, forget about the phase, you should be able to see that the line voltage VAB equals to square root of 3 times the phase voltage. Yeah, so you have this equation at the bottom, which will be the generic equation for each of the phase. Yeah, VLL is equal to square root 3 times the phase voltage V pi. Yeah. And from here we can see that the line voltage is not the same as the phase voltage, and also we can see that the line voltage is larger, yeah, than the phase voltage. Okay, that was the relation for the magnitudes. Yeah, for the phase, from the equation we can see that the line voltages are shifted by 30 degrees with respect to the phase voltages. Yeah. as you can see from this. Yeah. And then for the plots, yeah, for example, when we have this is VA n, yeah, and this VBN. So the line, these are the phase voltages. The line voltage for this between these two phases will be VAB, which is represented by this vector, and this has an angle of 30 degrees. Yeah. Okay, and then a similar case for the other two line voltages as well. Okay, note that using ABC, this is the one that we find when we use the ABC phase sequence. Yeah, which results in the voltage of a line leads the corresponding phase voltage by 30 degrees. Yeah. But when we use the other sequence, which is ACB, the voltage, the line voltage will be lagging the corresponding phase by 30 degrees. Yeah. So for example, VAB will be in this direction. Yeah. Okay. Did with the Y connection. Okay, the diagram shows us a three-phase generator connected in a delta configuration, connected to a resistive load. Okay, and because the loads are resistive, the currents will have the same angle, the same phase as the voltages. Okay, any line-to-line voltage between any two lines is the same as the phase voltage. Yeah. As we can see from the diagram, schematic diagram. For example, here in the yellow shaded area, the delta connection for the VAB, the phase voltage AB, will be this voltage here, and then the line voltage will be across these two lines. And as we can see, these two must be the same, yeah, because they are actually connected together. Yeah, I mean the top here is connected to this, so these two voltages will be the same, and similarly the bottom part here are also connected, and therefore the phase voltage will be equal to the phase voltage, and this will apply in the same way to the other phases as well. Okay, how about the current? Right. Okay, IA, yeah, if you look at this equation, IA is equals to IAB minus ICA. This comes from KCL. Yeah. If you look at the schematic diagram, then using the KCL for this node, yeah, node A, we can see that the sum of the currents entering the node will be the same as the total currents leaving the node. So the current that entering the node is IAB, leaving is IA and ICA. Okay, and then if you rearrange this, you should be able to get this equation. Okay, then you can work it out step by step to get this simplified form. You should be able to get this. Okay, and then for the magnitudes, we'll have this relation, and this will apply to all of the three phases. Yeah, the IL or the line current is equal to square root of 3 times the phase current. Yeah. Okay, so if you notice, this is like the opposite to the Y connection. In the Y connection, the currents are the same, but the line voltage is equal to square root of 3 times the phase voltage. For the delta connection, is the other way around. The voltages are the same, but the line current is square root of 3 times the phase current. And not only the magnitudes are different, but the phase is also different for the currents. Yeah? The line currents are shifted by 30 degrees with respect to the phase currents. And now this table shows us the summary, the relations between the line quantities and the phase quantities for both connections, the Y and delta connections. Okay, now in this section we are going to look at the power relations for these AC, three-phase AC systems. Okay, now assuming we have three-phase voltage supplies connected to load with impedance Z, then the equations for the three-phase voltages are given here. Yeah. And then we can derive the currents by dividing these voltages with the impedance Z. Yeah. And theta is the angle of the impedance. Right. Then we can derive the instantaneous power, yeah, by simply multiplying the voltages with the currents. So we have three powers, one for each phase. Yeah. This is all the instantaneous power. Now, next step, if we use this trigonometry identity, then we can transform these equations into this tree. Yeah. Then on the following slide, we will calculate the total of these three powers by adding them up together. So PA plus PB plus PC. And what do we get? We will look at the following slide. Right, now if we add them up together, all these powers, PA, PB and PC, to give us the total power, then we come up with a simple expression which is 3VI cos theta, which is interestingly constant. Yeah? There is no longer a variable t in the equation, but simply it's just 3VI cos theta. Yeah? And then if you look at the plots, then we've got phase A, which is this is the power for phase A, and then phase B, and then phase C, yeah, which are all sinusoidal, but when we add them up, we get this straight line, and this is the total power, P tot. Yeah? And again, it's constant, and really this is the second advantage of the three-phase system, which is it's able to deliver constant power rather than pulsing power that we have if we use a single-phase system. Yeah. And then the real power is equals to 3V pi times I pi cos theta, and then if we use the same method, we can derive the Q, the reactive power, and also S, the apparent power. And then from these three equations, we can also derive these three equations by using the equation that V is equals to current times impedance. Yeah. Okay, the equations on the previous slide were the powers, the equations for the powers in terms of phase quantities. So we use phase quantities. I've already copied the equations and I put them here. Yeah, you can see that we are using phase quantities, yeah, in these equations, yeah, and this too as well. We can rewrite these equations in terms of line quantities as well. Yeah. So from there we can derive these three equations, and now they are all using the line quantities. Yeah. And then how do you derive them? For example, let's remember this applies for both y and delta. But let's take one example. Yeah. Let's say we've got the delta configuration. Then in delta configuration, the VLL or line voltage is equal to the phase voltage. Yeah. In case you forgot, you can check the table that we had before, yeah, summarizing the relations between the line quantities and the phase quantities for both configurations. Okay, and then again as well for the delta, the line current is equals to square root of 3 times I phase. Okay, so if we rearrange this for I pi will be equals to IL over square root of 3. Okay, so now if we substitute VLL with this, the other way around, substitute the phase voltage with VLL and substitute I phase with IL over square root of 3, yeah, for this equation that we should get P equal to VLL times, I missed the number 3, yeah, 3, and V pi equals to VLL, and I pi is equals to IL divided by square root of 3 into cos theta. Okay, and 3 divided by square root of 3 is square root of 3 times VLL times IL times cos theta, and this is our P, which is equals to this equation. Okay, and again in a similar way you can also derive the Q and S. Yeah? Now we are going to look at briefly the analysis of balanced three-phase systems. Okay, in balanced systems it is possible to analyze a circuit consisting of one phase and the neutral, also known as per phase equivalent circuit, and the results of that will be valid for the other two phases. For example, we have this three-phase system, yeah, with the three-phase generators, and then we got the transmission lines, yeah, and then the three-phase load. Okay, and then we can to analyze this assuming they are balanced, yeah, it's a balanced system, we can then simplify it into the per phase equivalent circuit to do the analysis. Yeah. So this we can use this per phase equivalent circuit. If for the transformation, we can start from here to this, yeah, by adding the neutral line or the return line, yeah, and then just take one loop. For example, this loop here to becomes our per phase equivalent circuit, and all the magnitudes are retained. Yeah. So the impedance, for example, here has not changed, still the same, and the voltage also is equal to the phase voltage in the original configuration. And same thing with the transmission line. Whatever impedance you've got for the transmission line in the original circuit here will be you will have the same impedance for the per phase equivalent circuit transmission line. If for example you have a delta connected rather than Y connected load, then you can convert it first by using this equation here, that the impedance ZY, Y is referring to the type of connection, yeah, is equals to Z delta divided by 3. Yeah. So if you have this sort of configuration, yeah, with the impedance of Z pi for each phase, then you can convert it or transform it into this Y connection, but for each phase of the load you will have Z pi over 3 instead of Z pi. Then after that, just like what we saw on the previous slide, we can then get the per phase equivalent circuit to do the analysis of the three-phase system. Okay, we may you can have a look at the examples. There are two examples, but they are not covered in this video. There could be another video show us the steps by steps work to go through the two examples regarding the analysis of balanced systems. Thank you.